Math 2414, Calculus 2, Section 9.2, Calculus with Parametric Curves. Video 4 of 9, example number 2. In the previous video, we picked up some information that we didn't get to in 9.1, namely what's a cycloid and what are the parametric equations that define the curve. Just to recap real quick, a cycloid is the shape you get when you start with a circle sitting on the x-axis, so tangent to the origin, and then you keep track of the path the point at the origin takes as you roll that circle along the x-axis. This isn't the same picture as before, it's missing a lot of the pieces, but in general, theta being the angle of rotation is our parameter, and we're trying to keep track of the point x comma y based on how far we've rolled. Above here were the parametric equations of a cycloid. X of theta is equal to r times theta minus sine theta, where r is the radius of the circle, and y of theta is r times 1 minus cosine theta. Again, r is the radius of the circle, and theta is the angle in radians that the circle is rotated so far. In this example, we're going to do a couple of things with the cycloid. A, find the equation of the tangent line at the point on a cycloid where theta is equal to pi over 3. And B, at what points are the tangent lines horizontal and vertical? Notice I didn't specify a particular radius, so we're going to do this in general with r as a constant in our parametric equations. Also, it's worth mentioning that at the end of the previous video, we did conjecture the answer to part B. We conjecture that it takes one complete revolution for the point on the origin to go back to the x-axis. So we were conjecturing that 2 pi is where we start over, and hence 4 pi. And we also conjectured reasonably that halfway between its journey, the point on the origin will reach its peak at pi and over here at 3 pi. So I'm suspecting the answers to B for the horizontal tangent lines to be at pi, 3 pi, 5 pi, etc., odd multiples of pi. And I'm expecting the vertical tangents to be at 0, 2 pi, 4 pi, or even multiples of pi. But let's verify that this is true based on the calculus, not just based on speculation. But first, let's start with A. Find the equation of the tangent line at the point on a cycloid where theta equals pi over 3. As with most lines, if we have a point and a line, a point and a slope, we can find the equation of the line. So let's start with the point. All we're given is that theta is equal to pi over 3. Well, based on our parametric equations for a cycloid, we can figure out the x-coordinate and the y-coordinate. The x-coordinate would be r, which is a constant that we don't know, times theta minus sine of theta, or in this case, pi over 3 minus sine of pi over 3. Well, pi over 3 is just 60 degrees, and that's an angle that we know something about. Sine of 60 degrees is the square root of 3 over 2. That's about as far as we can push that. I guess you could argue getting a common denominator, but it's not going to make it any better, just look different. But we also need to know the y-coordinate at pi over 3. And at pi over 3, our y-coordinate is r times 1 minus cosine of theta. So in this case, r times 1 minus cosine of pi over 3. Pi over 3, or 60 degrees if that's in your comfort zone, the cosine of that is 1/2. This one's a little easier to finish. 1 minus a half is a half, and r times 1/2 is r over 2. So the point at pi over 3 is going to be, the x-coordinate is inconvenient, r times pi over 3 minus square root of 3 over 2, comma, but the y-coordinate is pretty easy, it's just r over 2, or 1/2 r. I think I'll write it as 1/2 r since both of these are a constant times r. All right, so we have our point, but now we need a slope. And remember, to calculate the slope, we want to know what dy dx equals. However, we don't have y as a function of x. In fact, it would be possible to get y as a function of x because it would be impossible to solve this first parametric equation for theta without getting into the details, you can't exactly solve for a variable that is both inside a trig function and outside it at the same time. I'm sure there are very rare exceptions, but as a rule of thumb, can't do it. However, we can find dy dx by simply calculating dy d theta and comparing it to dx d theta, as discussed in the first video. Okay, so what is the derivative of y with respect to theta? Well, this is a constant multiple, so r sits there. On the inside, the derivative of 1 is 0. The derivative of negative cosine is sine. So we just get r sine theta on top. In the denominator, we calculate the derivative of x with respect to theta. So it's going to be r times something. The derivative of theta with respect to theta is 1. The derivative of sine with respect to theta is cosine theta. And so we get 1 minus cosine theta. Look at that, the r's cancel, since they're both factors in their respective sides of the fraction, leaving us sine of theta over 1 minus cosine theta. Notice that the slope of the tangent line doesn't depend on r anymore. It only depends upon how far we've rotated. Speaking of the slope of the tangent line, we're still looking at theta equals pi over 3. This implies that our slope, dy dx, is going to be sine of pi over 3 over 1 minus cosine pi over 3. Well, sine of pi over 3 is still square root of 3 over 2. Cosine of pi over 3 is still 1/2. 1 minus 1/2 is 1/2. And if we multiply the numerator by the reciprocal of the denominator, the 2's would cancel, and we would just be left with the slope of square root of 3. All right, looks like we have what we want. Before we stick it over there and say we're done, let's build our equation and see how ugly it's going to get. I'm going to move the slope up here underneath the point. Slope is the square root of 3. So that I can erase this and now build the equation in point slope form. We have our point, we have our slope. Point slope form is y minus the y coordinate of the point, so y minus 1/2 r, equals the slope, square root of 3, times x minus the x coordinate. So x minus r times the quantity, pi over 3 minus the square root of 3 over 2. At this point, I'm wondering if there's really anything we can do to clean this up. I guess we could maybe get it in slope-intercept form, but in order to do that, we need to bust open all these parentheses. So we'll start by distributing the negative r. Y minus 1/2 r equals the square root of 3 times x minus pi over 3 times r, plus square root of 3 over 2 times r. Okay? And now we can distribute the square root of 3 to get rid of the other parentheses. Y minus 1/2 r equals the square root of 3 times x minus, all right, we just got a big mess here. We'll say pi square root of 3 over 3r plus, there's a small ray of sunshine here. When we distribute the square root of 3 to the third term in the parentheses, square root of 3 times the square root of 3 is 3, and we get 3/2 r. Which is actually not a bad thing to happen, because to get it in slope-intercept form, I'd have to add 1/2 r to both sides, and it just so happens that I have another r term over here to combine it with, and when I combine them, I get an integer. Y equals the square root of 3x minus pi times the square root of 3 over 3 plus 2r. There are other forms we could get it in. We could get it in standard form by moving the x and the y on one side of the equal sign and everything else on the other. Possibly clear out fractions, but I think the only other pretty version of this would be to move the y over here. That'll make it negative. Move all these over here, and then multiply everything by 3. If we did that, let's just keep track of everything. The y moving over here would become negative and multiply by 3 to clear out the fraction. The square root of 3x would stay over here but get multiplied by 3 when we cleared out the fraction. And then these other two terms we can move over and multiply by 3. The fraction would become positive and lose its denominator. We get pi square root of 3. The 2r would become negative and get multiplied by 3, becoming a negative 6r. As messy as it looks, this isn't that bad of an equation. It is in what's considered general form. which is a weak form, just get everything on one side, or all the variables on one side. And I cleared out the fractions just because good. Keep in mind that pi times the square root of 3 minus 6r is a constant because the radius is a constant. We just don't know what it equals. So either of these answers are okay. Either slope-intercept form, y equals mx plus some SEB, or general form, some x's plus or minus some y's equals a constant. All right, so we got the answer to part A. Let's write the answer in in general form. 3 square root of 3x minus 3y equals pi times the square root of 3 minus 6r. Part B. At what points are the tangent lines horizontal and vertical? Remember, for a horizontal tangent line, the y-coordinate has to have a velocity of 0. In other words, the y derivative has to equal 0. And for a vertical tangent line, the x-coordinate has to stop. Its velocity has to be 0. So we set dx dt is equal to 0. Horizontal. We need the derivative of the y parametric equation with, these aren't t's, these are thetas. And we need to put that equal to 0. The derivative of our y equation, as we found earlier, was r times 1 minus, back. I'm looking at the wrong equation. The derivative of the y equation, r is a constant multiple. The derivative of 1 is 0, the derivative of negative cosine is sine. So we have r sine of theta is equal to 0. Since r is the radius, we're assuming it's not 0, so this implies that we can divide both sides by r, get sine of theta is equal to 0. That's easy. Or on the unit circle, is sine equal to 0. Remember, on a unit circle, the sine of the angle is the y-coordinate. There are two places on the unit circle where the y-coordinate is 0. On the right side and on the left side. On the right side, we start with 0. On the left side, we get pi. That doesn't sound right. Theta equals 0. Yes. Pi. Yes. 2 pi. Yes. 3 pi. Yes. 4 pi. You'll see why I'm hesitant here. What we seem to be getting is that there's a horizontal tangent line at every multiple of pi. Well, there's not one here. At 2 pi, at 0 pi, at 4 pi. But let's keep analyzing, because remember what we said in the first video. To be a horizontal or tangent line, one derivative must be 0, but not the other. So let's figure out the verticals and see if we have both derivatives being 0 simultaneously. For the vertical tangent lines, we need the derivative of the x parametric equation to equal 0. dx d theta is equal to 0. Well, the derivative of our x equation is r times 1 minus cosine theta. We need r times 1 minus cosine theta to equal 0. Again, assuming that the radius isn't 0, otherwise there would be no circle to move. We could divide both sides by r and get 1 minus cosine theta is equal to 0. This implies cosine of theta is equal to 1, and where on the unit circle is cosine equal to 1? Cosine is the x-coordinate, so it's over here at 0, at 2 pi, at 4 pi, and all of our even multiples of pi. Theta is equal to 0, 2 pi, 4 pi, etc. All right, so we do have a conflict. We have values of theta where both derivatives are 0 simultaneously, where both the y and the x are changing. And it kind of makes sense if you think about it. Because at 2 pi, isn't the y slowing down and having a velocity of 0? And the x is 2, but then it's going to resume. So let's look at the ones that aren't a conflict. The ones that aren't a conflict are where the derivative of y is equal to 0, but not x. That would be the odd multiples of pi. So, at odd multiples of pi, we have dy d theta is equal to 0, and dx d theta is not equal to 0. That was only the even multiples. Therefore, we can instantly conclude that there's a horizontal tangents, or there's horizontal tangents at theta equals all the odd multiples of pi, which we can write as 2n plus 1 times pi, where n is an element of the integers. For my current Cal 2 class, I'm not sure if I've used this recently, the double script z, meaning the set of integers. This just means any number you can count with, positive or negative. So if I put in 0, 1, 2, or 3, this is an odd number. We pick up all the odd multiples of pi. But that leaves the even multiples of pi. When the derivatives are simultaneously 0, as they are at even multiples of pi, you can't conclude horizontal or vertical tangent lines at that point. You can't say that that it's inconclusive and you need more evidence. So what can we do? Well, if you recall, the derivative at its core is a limit as something approaches 0. So why don't we look at the limit of our derivative, dy dx, as we approach one of the values that's causing both derivatives to be 0 simultaneously. And my apologies for bringing up that a limit is defined as something approaches 0. Yes, that's true, but it's not what we need now. When your derivatives are simultaneously 0, you need to analyze the derivative a little bit more closely by approaching those values, or at least that's one thing you can do. So let's move our derivatives up here. Well, I can restart it. Remember, we're looking at even multiples of pi. And I think it's reasonable that whatever we conclude for one of them is going to be true for all of them because of the periodic nature of this graph. Recall that dy dx is dy d theta over dx d theta. We used that in the first part of this question, part A. Our dy d theta was r sine theta. Our dx d theta was r times 1 minus cosine theta. The r's cancel. And we have sine theta over 1 minus cosine theta. And we want to know what this equals at even multiples of pi, because that's what made both sides 0 simultaneously. Wait a second. Both sides are 0 simultaneously. That screams L'Hopital's rule. If we take the limit as theta approaches one of those even multiples of pi, it doesn't matter which one because of the periodic nature, so let's choose 0. If we take the limit as theta approaches 0 of dy dx, we're taking the limit as theta approaches 0 of sine of theta over 1 minus cosine theta, but that'll give us 0 on both sides, screaming L'Hopital's rule. So let's do L'Hopital's rule and say that this limit equals the limit as theta approaches 0 of the derivatives of both sides of this. Well, on the top, the derivative of sine is cosine. And on the bottom, the derivative of 1 minus cosine theta is just sine. Derivative of 1 is 0. Derivative of negative cosine is sine. Can we just plug 0 into this? Well, we would get 1 over 0, at which point we have to stop. If we tried plugging in 1 over 0, well, we can say that's infinity, but now we have to be really careful. Because if we were to come in from the left side of 0, our slopes would be negative and getting more and more vertical, closer to negative infinity. And if we were coming in from the right side of 0, then our slopes would be positive and getting steeper and steeper and becoming closer and closer to positive infinity. So maybe we need to analyze this a little bit more closely in terms of coming in from one side of 0. If we come in from the left side of 0, the right side of 0, our slopes are approaching positive infinity. So let's amend this to say approaching 0 from the right, and now we can say that this approaches infinity, which is basically what says your vertical tangent line. Recall that a vertical line has an undefined slope. That's because if you rotate this way, your slopes are getting larger and larger positively, positive infinity. But if you rotate this way, your slopes are getting larger and larger negatively, negative infinity. but either way, you get a vertical tangent line. So the vertical tangent lines took a little bit more analysis because both the both the derivatives of x and y were 0 simultaneously. But by taking the limit as we approach one of those even multiples of pi from the right of the slope, we got an opportunity to use L'Hopital's rule, and then we had to analyze it even deeper because we had 1 over 0, which means either infinity or negative infinity, depending upon which side you're coming in from. But if you put all that together, that means at even multiples of pi, dy d theta equals 0, and dx d theta equals 0, which means it's inconclusive, but using the limit as x approaches 0 from the right of dy dx, and in parentheses, and L'Hopital's rule, we conclude vertical tangents at theta equals 2n pi, even number times pi. Again, n is an element of the integers. So that one took a little bit more of analysis, but it does answer the question, what happens if both derivatives are 0 simultaneously? You take the limit as you approach the value of the parameter. Let me point to the board while I'm saying this. You take the limit as the parameter approaches that value that makes both derivatives simultaneously. You should probably do it from one side or the other from the beginning of the slope, which is just the ratio of the derivatives of the parametric equations. If you get an answer, great. If you get something that's L'Hopital's rule, that's okay. Hit it with L'Hopital's rule. But if you get something with 0 on the bottom but not on the top, then you have to analyze it by approaching the limit from the left to the right. Very analytical, but then again, you're at the tail end of calculus 2. The analysis can't intimidate you. Ooh, that was a long video.